So thank you for the nice introduction. So first of all, I'd like to thank the organizers for the conference and the steering committee for inviting me here. And so it's been very nice up to now. So yeah, and I think it's really a very nice conference. And so today I'm going to talk about quantum algorithm for codes and lattice based on Regev's reduction. And so I'm going indeed to present some of my recent work of Jean-Pierre Tillich, but also do like a general overview of this new family of algorithms like for these problems. Okay, so what's the general context of the of this algorithm? Okay, so we know that Shor's algorithm threatens an important part of public key cryptography, and if we consider this as a serious threat, then we have to anticipate a long time in advance. Well, first of all, because it takes some time to change the cryptography to something that doesn't rely on factoring. Second of all, because you have these store now, decrypt later attacks, right? If you think that a quantum computer will come in 20 years and that will break RSA, then someone can store encrypted messages now and decrypt them in 20 years when the quantum computer comes, right? And so that's a little bit annoying. So it's not that you have to be ready when the quantum computer arrives, but if you want to preserve current data from future attacks, then you have to have a long time in advance. So but like, okay, so now we have to commit on other computational problems on which we build cryptography and that we believe are hard for quantum computers, right? That we don't have an equivalent of Shor's algorithm for these other computational problems in a few years, right? Otherwise, all the effort goes down to nothing, and we have to start from zero. And okay, so ideally, we'd like to have like complexity theorems that say, this problem is hard for quantum computers. But this is very, very far from our reach, right? The problems that are used in cryptography, they're at least in NP. And so first of all, we don't know if NP is different from P. And even so, those problems, and on top of that, they're not NP hard. On average, usually they're average case problems. So they're somewhere in NP. So it's very hard to say whether they're hard classically. And it's also very hard to say whether they're hard quantumly, right? Okay, and so so knowing that there will be likely some breakthroughs in quantum algorithms, so the question is, will these breakthroughs attack directly like these new computational problems that are used in post-quantum crypto, right? So that's kind of one of the questions. And okay, so but let's see how we're doing now. So the NIST launched a call like a few years now. Maybe it's been like quite some, maybe 8 years now. I don't remember. A call to standardize post-quantum cryptography. So encryption schemes, signature schemes, which rely on computational assumptions that are not broken by quantum computers, that we hope are not broken by quantum computers. And so, okay, so there are many different submissions. So based on Euclidean lattices, error-correcting codes, isogenies, multivariate polynomials. And okay, and so let's see all of these problems, like, did we manage to find the quantum attacks? Well, the answer is not really, right? There have been many submissions. And when you submit a real encryption scheme or a real signature scheme, okay, you always add some structure. You want to be very efficient. So you add some more structure to be more efficient. You're very aggressive on your parameters. And sometimes you just have flawed design. So a good portion of those schemes were actually attacked, but they were all attacked by classical attacks, right? So there wasn't one scheme that was classically secure, that proposed scheme that was classically secure, but that was totally broken by quantum computers, right? I'm talking here about like very big, like total collapses, right, of the schemes, not just like maybe minor improvement in the algorithm, but really like major breaks. If you have a major break, it's because you have a problem, but the major break also appears classically, right? So that shows us that, okay, if we can handle like those problems, like, okay, this lattice-based crypto, code-based crypto, if we do it well, and we do it in a way we believe is secure against classical computers, then, okay, the security somehow translates to quantum computers as well. So that gives us a strong, a belief that, okay, these problems, they seem also hard for quantum computers. And okay, and so in this talk, I'm going to focus on code-based and lattice-based, but okay, they're actually very close cousins. So okay, at a very high level for now, what are the code problems that I'm going to be talk about? So you take a code. So take your favorite error correcting code. So you can take a random linear code, a binary code, query code, whatever. So you have a description of a code, and the decoding problem is I give you a code word, in a code word from which there was a little bit of noise added, and the goal is to recover the code word, right? So this is the standard decoding problem that arises like in telecommunication. That's kind of the historic problem, is that I want to send you a message through a channel on which there can be noise. So I encode my message into a code word, then the code word goes through the channel. There's a little bit of noise on the code word, but because of the structure of the code, I can recover my original code word from which I can recover the message, right? So if the code word has a little bit of errors, then you want to find a code word for which you can decode, right? So this is the first problem. So historically, we're trying to design codes for which this problem is easy, right? Because when we do transmission, but it's also a problem that was used in cryptographic protocol, because, for example, for random codes, this problem is hard. Like even with a small, let's say, constant fraction of errors, if you take a random binary linear code of constant rate, let's say, then this problem will already be hard, right? So that's the first kind of family of problems that we're looking at. And the second family of problems is, okay, it doesn't directly arise from telecommunications, but it's the short code word problem, is that I give you the description of a code, of a linear code, let's say, so of a linear code, and the goal is to find a short code word from this code, okay. Because the 0 word is always in the code, okay, well, that's a short code word for sure, but okay, so you want a short non-zero code word of the code, right? And so you have these two families of problems, and I wrote them that one is in the injective regime and the other one is the surjective regime, because the parameters will consider the first problem, the error will always be kind of small enough that you have one solution which is the closest, that with very high probability, like from an information theoretic point of view, you know from which code word you come from. And on the other side, like we're in the surjective regime, because in this red region, there's actually an exponential number of solutions, right, to this problem. So this is kind of the parameter that we'll be looking at. And as I told you in the beginning, these problems, they're close cousins to lattice-based problems. So if you're more familiar with lattice-based, you can basically see the decoding problem as a learning with errors problem in lattices, and the short code word problem as a short integer solution problem, right? So and there are many variants, so in both coding and lattices, there are many variants, but like basically, these are the two big families of computational problems that we want to deal with. And these problems for random code or for some structured codes, we believe that they're hard for classical computers and hence for quantum computers. Okay. So now that we have this general overview of what are these code problems, so the postulate of post-quantum crypto, and here for let's say a code base and lattice base, is that if you have this orange region of problems, of computational problems that we use in crypto, then okay, the problems that are easy for quantum computers, the purple region does not go in the orange circle, right? If you have a purple point that arrives in the orange region, you break some part of post-quantum crypto, right? But okay. So this is like basically the main postulate, but actually we have also like stronger beliefs that this family of decoding problems are hard, because even if you consider other decoding problems for other parameters, which are not necessarily used in crypto, but because there are many, many variants that you can define, the problems that are classically hard, we also believe them to be quantumly hard. So in some sense, the whole family of problems, not only the ones you use in crypto, but the large family of decoding problems, short integer solution problems, and associated, if they're hard for classical computers, they're hard for quantum computers, right? And so this kind of tells us, okay, this whole family is kind of safe for now. But okay, things are starting to change a little bit. So what happened is that Chailloux, André, so the archive version 21, but the published version 22, they showed how to solve a short integer solution in infinity norm in a somewhat contrived parameter regime, but that we didn't know how to solve with classical computers, right? So that we don't know how to solve with classical computers, and it's a very contrived regime, but it was a first little scratch on this blue region already, right? That we had. And then a year later, Yamakawa and Zanri, they showed how to solve a problem on structure code. So it's relative to a random oracle, but they actually show in the random oracle model, they can provably show that you have a quantum advantage for this problem. And this result, like this quantum advantage without structure, also is one result from this family of algorithms that I'll present. And then there has been like, okay, few more like dots popping. So there was this decoded quantum interferometry paper by Jordan et al. That solved some decoding type problems. So in the surjective regime, so in the second regime, for Reed-Solomon codes and low density parity check codes, right? And also in some regimes that, okay, we don't know, we're not sure like whether we can solve them with classical computers as well. And with Jean-Pierre Tillich, we also showed how to improve like this result on Reed-Solomon codes by allowing the use of soft decoders, so which is something I'm going to talk about. So, okay, you have these little purple points that that come in this blue region. So, okay, so we're a little bit unhappy. Okay, and so what's going on? So, what was this? Okay, so how all of this is done? So all of these results, they basically use one family of quantum algorithms, which are based on Regev's reduction. So Regev's reduction is from like 2005, so it's a fairly old reduction, and it's one of the cornerstones of lattice-based cryptography. But it's not an algorithm; it's actually a complexity reduction to show that some learning with errors problem is harder than some problems, lattice problems, like related to the short integer solution problems. And from this family of, from this reduction, there has been also more follow-up work. So Debris, Alazar, Remo, and Tillich showed how to extend this to the code-based setting. With Jean-Pierre Tillich, we also showed how to improve this reduction by the study of the quantum decoding problem, which I also talk about. And there has also been applications to oblivious sampling. So, you know, even applications outside of purely like algorithm and trying to show quantum advantage could be done using this framework. Okay, so so I guess it's a long talk, so we have time. And actually, this Regev's reduction, it's not something which is overly complicated. So it's something which I have time to explain during the talk. So at least hopefully you will have a first glimpse of like what this family of quantum algorithms look like. Okay, so I will write it in the context of codes. So I talk from a Curie linear code of dimension k and length n. So, and you characterize it by a generating matrix G. So you have a k by n matrix of k lines and columns, and your code is basically a linear combination in FQ of the lines, right? If you're more familiar with binary codes, then you can think of binary codes. It's all fine. If you're more familiar with Euclidean lattices, and what I will say also hold for Euclidean lattices, right? But so you have this matrix G, and you know, if you multiply, so here the vectors are line vectors. So if you multiply, you take all the linear combinations of the lines of G, then this generates you a Curie linear code, right? So this code can be specified by a generating matrix. You can also see a code as the kernel of some parity matrix H. And so, okay, so both of full rank here. And also for a code, we associate a dual code, which is consists of all the words which are orthogonal. So like the inner product here in canonical product, inner product of FQN with each code word. Okay, so these are like basic definition for codes. Okay, so here I recall the two problems. Now that we have this code, okay, so basically this problem is that you're given, when I say you have a code, so it's specified by a generating matrix, and you have these two problems that I remind you, the one in the injective regime and the one in the surjective regime, the decoding problem and the short code word problem. And okay, and so what does Regev's reduction do actually? Okay, so this is a much more, it's a modernized version, so maybe the one from like the DRT, the Debris, Alazar, Remo, Tillich, maybe a formulation, is that if we have an efficient algorithm that solves the decoding problem for a certain error distribution, right? So I told you there is an error, so it's taken from a certain probability distribution. So you have this function f. We'll see why we take this function f, because then we'll do quantum. So we prefer work with amplitudes and with the probabilities. But you take a function f so that its square module is a probability distribution of the errors. And I say, okay, if I give you a code and a probability distribution, and if you have an algorithm that can solve the decoding problem with this error distribution, then I can find short words in the dual code, right? And what will be the weight of the dual code? Well, it will be a function that depends on the Fourier transform f hat, so it's the Fourier transform on FQN. And so you have this function, take it for your transform, and somehow this will define the weight of the word you get in the dual, right? So you can phrase it as this sampling problem that you can sample from the dual code with respect to this module of f hat square. So you normalize the f hat so that it's also a property distribution, and you take the restriction on the dual code. It gives you a property distribution on the dual code, and the algorithm allows you to sample from this distribution, right? But if you want to just look at it in simpler terms, if f hat, the image, is restricted in words of small weight t, then you obtain a dual code word with weight at most t, right? And I didn't specify the norm, but it can be for any norm. It works for the Hamming weight, 2 norm, infinity norm, whatever, right? So I didn't specify because this is totally independent of what kind of thing you actually choose, right? This is a very general reduction. Okay, so this is a rephrasing, and it's a very clean algorithm that I'm going to present you now. Okay, so it consists of 2 simple steps. So I start, so remember, I have an algorithm for the decoding problem, and I want to construct a quantum algorithm to find short code words in the dual code. So the first thing is that I will use this decoding algorithm to construct this state on the bottom left, which is a superposition of code words and errors like this, like in quantum superposition. And then the step 2 will just be I apply a quantum Fourier transform and I measure, right? So actually, all of the important part will be in the first step, and the second step will just be a direct kind of quantum Fourier transform. Okay, so these are the 2 main steps. So now let's go and see what's the first step. Okay, so I said I have a quantum algorithm for decoding, so let's be slightly more formal. So here I just wrote the definition of the decoding problem, but which is basically the formal thing of what you said. You have, your a fixed generating matrix. I give you a random code word. So how do I generate a random code word? You generate a random S and you multiply it by G. So G is public, S is secret. You sample a random error from the property distribution P, and given the description of the code and the noisy code word, you have to recover the code word. And what does it mean that I have an algorithm that does this? It means that for any code word and for any E taken from distribution P, we have that A of C plus E output C, right? So here we consider the simplified setting where the algorithm perfect, right? So then we'll see what happens if we add some errors, but here it will be much easier to look at the perfect setting, and this is this is how we define a decoding algorithm. And okay, and so now we'll see how we do the step 1 of Regev's reduction. So on the left is what we want to do, and on the right is the different steps. And so as you can see, there are not that many steps. So the first thing you do is that you create a uniform superposition of code words and the superposition of the error function. So okay, the superposition of the code words, you can do it quite easily when you have the generating matrix G. So because you can you can construct this random S, you can construct SG, and then from SG you can also recover S. So by Gaussian elimination, this is something that we can easily do from the matrix G. And the superposition of the error function, well, okay, assume you have an error function f for which this is easily computable. Usually our error function will be very simple, so this will not be an issue. Okay. Then we do simple manipulation. So we add the first register to the second register. We swap. We add a minus sign. So okay, this is all elementary operations. Okay, and now the key part is that we'll apply coherently or a decoder, right? So let's say we have a classical decoder, so we apply it, let's say, coherently. So it uses the first register as a control register, and it adds the output of the algorithm to the second register. Right? So you do A of C plus E, and because we had a minus C, then the second register is now 0, right? Because we say we always have A of C plus E, which is equal to C. So the second register is 0, we discard, and we have our state, which is kind of exactly the state that we have on the left. And so somehow, this is maybe reminiscent of other problems we have in quantum algorithm, is that when you look at the state we have at step 2, there is this second register, and it annoys us. We want to erase the second register, right? And in quantum algorithm, it's often something we want to do, and it's often something we cannot do, right? But here we're in this setting is that we use kind of a cheat code, which is this quantum or this classical or quantum algorithm for decoding in order to erase the second register, right? And then we're left with this state on the bottom, right? So it's really like these simple steps, and we already have most part of this algorithm based on Regev's reduction. Okay, And as I said, the second step, we just apply a quantum Fourier transform. So we constructed this state, which is, you can see it as the superposition of the green region. So let's say each of the green balls it corresponds to the errors. So let's say to the sum over E f of E E. And then we have also a sum over all the code words. So we kind of repeat this for all the code words. We add this little ball around the code, right? So we have this state, which is kind of correspond to this green region, this superposition of all the elements of the green region. And when we apply a quantum Fourier transform, you can do a simple calculation, is that you will get a superposition only over the dual words, but it will not be a uniform superposition. There will be weight amplitudes in front of each code word, depending on the Fourier transform of the function f, right? And so if we take, in particular, that's what we want to take f hat, which is concentrated around small weight words, so concentrated around 0. So okay, we don't want specifically 0, but we want, let's say, this word of small weight. Then if we choose this f hat like this, then we'll have this kind of picture, right? And so, okay, and just one way also to see the calculations, is that on the left-hand side, you can see the state that we have actually as a convolution between the indicator function of the code and the error function f, right? If you can compute this convolution, it gives you exactly the state above. And we know that after this quantum Fourier transform, a convolution is transformed into a product, right? So you get on the right side the product of the amplitudes, and you conclude just by saying that actually the Fourier transform, you get the product of the Fourier transform of the functions, and the Fourier transform on the indicator of the code is actually the indicator of the dual code, right? And so from this, you can recover the state on the top, right? Okay, so and once you have these calculations, you measure and you get this y in the dual code taken accordingly to this function, right? So the more this f hat is concentrated on small weight code words, the smaller weight code words you'll have. Okay, so this is the generic reduction. So okay, so in theory we know everything and everything is nice, but okay, so I did you the perfect setting, and okay, errors in the decoder. So usually when you have an error, like quantum algorithm, things are continuous. You put a small error. Okay, sometimes it's painful to analyze, but things usually go well. Here, it's one of the settings where it doesn't go well at all. And like the famous thing, like a tiny error in the decoder can cause a full collapse of the decoding algorithm. So like it's chaos, like in chaos theory and meteorology, like thing like that, right? Okay. So what happens when we have failure? So when our decoder, so we said I give you C plus E, this noisy code word, and it outputs you the code word. Okay. Let's say it has a small failure epsilon. So you have this function f. And so what happens is that you do it, and so it will not output you the thing with respect to some function f, but it will give you this sampling problem with respect to g hat. And okay, you have a small error epsilon, failure epsilon in your decoder, so g hat is close to f hat, right? This is absolutely no problem. The catch is that at the end, we don't have something which depends on f hat or g hat. We have something that depends on f hat or g hat restricted to the dual code. And here, you can have two functions which are very close, which are equal everywhere, but which are just very different on the dual code, right? And so that can happen. And what we showed, like in the first paper in the quantum decoding problem, we have examples where the failure in the decoder is negligible, but the two functions outputs you have are orthogonal, right? That you have so what you get is nowhere near what you wanted, right? You chose very carefully your function f so that you can decode. Your function f hat is exactly what you want. You're super happy. You're like, and then you have the decoder. You have a negligible probability of errors. You're like, okay, yeah, that's going to work. It will be a small error in the end. I'm happy. No, not at all, right? So you can find examples where there's a total collapse of this algorithm with this negligible thing, right? So yeah, so that's a bit of a problem, right? When we want to analyze. Yeah, so okay, and not allowing errors in the decoders put some strong constraint on the error function. Like so, if you have a code, so let's say you have a code and it has a minimal distance d, right? So if you have the minimal distance between two code words, let's say it's d. So if you want your algorithm to work really, really perfectly, you cannot go, the error must be at most d over 2, right? Or d over 2 minus 1, something like that. So that you really need the balls around the code words to be like totally disjoint, right? So that even from an information theoretic point of view, I'm not even talking about like efficiency, but even from an information theoretic point of view, having a decoder that works with property 1 limits the error distribution to errors of, at most d over 2, where d is the minimal distance of the code. But if you take a random code, actually, from an information theoretic point of view, you're in theory possible to decode up to d errors, d maybe minus little o of 1 or something like that, right? If you want to have it with very high probability. But if you allow even a negligible error, a property error, then okay, you can go from decoding from d over 2 to d essentially for random code. So it's a huge change. So like very small differences can do very big changes here. So it's quite a big deal that we don't allow errors in the decoder. So the consequences, so the papers usually they didn't, so they did use decoders. They would, because you need the stronger decoder to have the better algorithm you'll get. Yeah? So what you do is that, okay, but I told you, okay, there are some examples where it doesn't work, but okay, of course there's some example where it does work, right? So it's not that it always fails. It's just that you can find some specific counterexamples where it fails, but it just means that you have to do the proof every time, right? We don't have a nice criterion which says, okay, well, this will always work, and something which is easily verifiable. For now, we don't have. We just have to do the analysis by hand, and the analysis is a little bit messy. If you can see that, okay, an epsilon, that there are some bad cases where the thing explodes, it's saying that there are some technical difficulties in kind of making the thing work. And actually, like, of all of those papers, like one of the main technical contributions, like, of all these papers is trying to prove that, okay, things go well, like with errors, right? But sometimes, it's too hard to handle, and and in some cases, for example, if you have a decoder that doesn't have errors, like for example with the Reed-Solomon codes, you have the Berlekamp-Welch decoder, and it decodes up to half of the minimal distance in an efficient way, and you're like, and you settle with this, and at least you get rid of all of these problems. Okay, so that's annoying, and if we have to do the proof each time, then it's a bit annoying. If we have to settle on worse decoder, it's annoying. So the solution we proposed with Jean-Pierre Tillich in the second paper, so quantum advantage from soft decoders, is to slightly change the problem we want to solve, and to go to this inhomogeneous setting, and then life will be easier again. So what's the inhomogeneous setting? So now I only look at this surjective problem, so at our target problem. So on the left, I put the short code word problem that I defined earlier. And then I'm going to define the inhomogeneous short code word problem, which is this problem, but you shift with a random y0, right? So instead of looking from a code word which is close to 0, or after the reduction, a dual code word which is close to 0, you're looking for a dual code word which is close to a randomly chosen point in the space, right? Which doesn't have to be a code word anymore. And so you choose a random y0 and ask you, find me a code word, dual code word close to y0, okay? And those two problems, if you look at them from how they're used in crypto and what do we believe about the complexity of this problem, they're essentially interchangeable, right? We don't have formal reduction really from one to the other, but all the algorithms that work for one work for the other, vice versa, and and we use and in crypto we often use the inhomogeneous version, and so from if you look in terms of post-quantum crypto, these two problems, they really look like equivalent. And this Regev's reduction, you can transform it to make it work also, to start from an algorithm for decoding into an algorithm that will solve the inhomogeneous short code word problem in the dual code, right? So if I give you a random y0, you can tweak a little bit. So this is a rewriting of the first step of the algorithm, where you add this phase omega to the minus y0 in your product with C. So okay, here I put a prime Q, so we have roots of unity. If you took a more general finite field, that you can replace this root of unity with the characters of the of FQ, and then it works the same, right? but okay, but here for simplicity, I only write it for Q. And so you just add this little phase at the beginning of the protocol. So Y0 is given to you, and C, you have it in a register. And then after the quantum Fourier transform, you get something which is shifted like this. And so what does this mean is that, okay, if f hat is concentrated around small weight code words, then what you measure here is a dual small weight words. Then the amplitude f hat y minus Y0 means that you'll measure dual code word y, which is close to Y0, right? So you did the shift in the way so that we get exactly what we want. And yeah, and so also just to see the second step, so the second step, you can just see it as the same picture as before, but we added this little complex phases on each of these balls, so it makes them a little bit different. And this allows you in the dual setting to have this concentration of weights in the dual code, but concentrated around this Y0. Okay? And so what we prove is that, okay, in this setting, there's no problem. Like if we want to reduce to the inhomogeneous setting, that, okay, if you have a decoder that has failure epsilon, then the algorithm I presented you outputs a string of small weight with probability 1 minus order of root epsilon. Whereas in the previous case, you could prove something like this, but you had a q to the power n that would pop up in the error, right? So you could make the thing like explode a lot. Whereas here you don't, you really have something which is continuous, and that corresponds more to like what we would hope, right? So if you have a small error, then it will work out. Okay, and so this picture is a generic recipe for constructing new quantum algorithms. So this is sometimes, so you know, sometimes I have a more classical audience, and I tell them, look, you can have on the top, you know, if you find a nice code and you find a nice classical algorithm for it, and you look at this dual problem, then and you think it's hard and you think it's an interesting problem, then you can build, you know, you can provide quantum advantage without knowing anything about quantum algorithms. Just if you find, you know, if you find good classical algorithm, so okay, you could find good quantum algorithm, of course, for the first part, but if you find good classical algorithm for decoding problem, and you know that the resulting problem, you know, is hard, or you believe it's hard, then, you know, you have a general recipe and it works, and, you know, so that's very nice. And so now, and essentially all the algorithms, so sometimes they don't work in the homogeneous setting, they prove algorithm for the homogeneous setting, but basically, you know, you follow this recipe. Of course, this recipe was not known before. Like this is from 25. This is from this year. So, but this kind of encompasses many of the of all of these papers that were here. Okay, so we have this recipe, and so let's try to see like how to, you know, let's try to instantiate in some sense this. Okay, so a first natural idea is to take structured codes for which we can easily decode, but for which we believe the, just look at, okay, no, I don't have the number here. Let me just see how far I look from the thing. Okay, so, so the idea is, so you want to take a code for which the decoding problem is easy, but for which the resulting problem you believe is hard, right? So, and there are candidates, and for example, in the decoded quantum interferometry paper, they looked at two cases. They looked at the LDPC codes for which we have heuristic algorithm, and Reed-Solomon codes for which we have efficient decoders. So in this talk, I'm going to talk about the second thing. So, okay, so just briefly to see like how an instantiation like this would work. So here we look at full support Reed-Solomon codes. And so the idea is that, okay, you take this finite field, and basically a code word of a full support Reed-Solomon code is just the images by a polynomial of degree at most k minus 1 of all the elements of the field. Right? So you just take, so a code word is just a list of all the images P of alpha for all the elements of the field. And if you consider the set of all the polynomials of degree strictly smaller than k, then this is linear, because if you sum two polynomials of degree at most k, you have a polynomial of degree at most k. And so we have, and so it constructs a code, and this is a very important code in coding theory. And we take this full support codes because it has the very simple property is that if you take the dual of a Reed-Solomon code with k, then it's also a full support Reed-Solomon code with q minus k. Right? So we have very simple proposition. And because, we need to look at the code and we need to look at this dual, right? So if they have kind of the same shape, then it's kind of easier to analyze. And okay, I'll go fast, but here we do have efficient decoders for this full support Reed-Solomon code. And some of them even have no failures, but then you have more advanced decoders that have failures. And especially the one that we looked, which was kind of gave the best performance, was the Kötter and Vardy, which didn't only look at how many errors you have, because we're in FQ, but really looks at the shape of the probability function, right? So really, okay, not only whether it's zero, it's change or not, but really, so it looks at more advanced kind of quantities on the error function, and in this case, it gave us like a much better result. And this is why, for example, in the paper we talked about soft decoder, because it uses soft information about the error. And so those decoders, they're very efficient in the injective regime. So we know how to decode, like these are really like non-trivial decoders, but they do not carry over to the surjective regime, right? So because we said, okay, like the dual code is also full support Reed-Solomon code, can we use them to find words which are like not too large, small code words? Then okay, we don't know how to do it. And so if we apply a recipe, so you can just take a code, and so this is basically rewriting of this 2 steps of Regev's reduction, but in this specific case. So basically what do we do is that we take a function, and so we're interested in f hat, right? It's f hat that gives you kind of the condition we want at the end. So let's say we want to solve like this inhomogeneous short code word problem, and let's say we take the infinity norm. So we take f hat, which is supported on words of small infinity norm R. And when we apply all of those steps, we add our little omega so that we're in the inhomogeneous setting. We apply the quantum Fourier transform, we measure, and we get a dual code word which is close to Y0 in infinity norm, right? And also what is nice for this problem is that why did we choose the infinity norm and stuff like that, is that it's actually, when you look at the problem we're solving, it's looked like a problem which is not at all a coding problem, right? I mean, okay, from coding, then you could see the links, but if you're outside of coding, if I tell you what problem we're solving, you don't immediately think of error correcting codes. And it can be seen as an approximate polynomial interpolation problem. So let's take as an example, so we take Q equals 7, R equals 1, and let's say Y0 is our target, and we want to find a point in this full support Reed-Solomon code of Q minus K, so this dual kind of Reed-Solomon code, such that it has an infinity norm close, one close to Y0, right? And so because we said like these code words of these full support Reed-Solomon codes, it's actually uniquely characterized by a polynomial of degree smaller than Q minus K, and the constraint, the infinity norm constraint, means that you have a constraint on each of the images of P of alpha for H alpha in FQ, and it means that your polynomial must pass. So in perfect interpolation, you would say, okay, I want my polynomial to pass through all of Y0, right? But okay, Y0 is a random, it's just a random point, and it goes through all the things. So you wouldn't expect, except with negligible probability, to find a polynomial of degree smaller than Q. But now you don't ask for perfect interpolation because you have Q points, right? So. But now you allow a little bit of margin on the interpolation. You don't want to go strict around Y0, but you allow, okay, you can be one higher or one lower, right? And this corresponds exactly to the infinity norm constraint, right? So the question is, okay, so I have a set of points, and I ask you to find a polynomial of low degree which passes not too far from each of the points, right? If you see it, it doesn't necessarily look like a coding problem, but it is a coding problem, right? And this algorithm that we do, Regev's reduction, is actually a quantum algorithm to solve this kind of problem, right? Okay, and so this is kind of the results we obtained. For example, depending the speed up, so we just looked at the ratio of this orange region from the whole space, and what is the degree we can get on the left, right? And so we show the difference. What happened if we use this Berlekamp-Welch decoder that only decodes up to d over 2, that doesn't have errors, and when we take better decoders, then okay, we have then we have smaller degrees, right? So in some sense, we have better results. And what's interesting is that classically, for any these problems are always exponential, right? So if you take this this fraction rho, which is kind of any kind of constant thing, then you cannot find classically polynomials which are degree like significantly smaller than q, whereas here you have a constant constant fraction of q for the degree. Okay, so that was just like one instantiation, and so yeah, like of this thinking for structured codes. Now, okay, and so I want to talk about, in the time that is left, about the second like important key idea of the related to this family of algorithms, is reshaping the error. So, and how to reshape the error with quantum information tools. And in a somewhat maybe surprising way from what we heard until now, I'm going to talk about an ambiguous state discrimination. Right? And so what does it have to do with everything that I've talked about until now? Okay, so let's go back to the first step. So here, just recall the first step. So you have this, and we say we use this decoder to erase the second register from step 2 in order to go down, right? So that's what we did. And now for each C, we'll define psi C, which is the superposition over all the errors of the state. And the decoder, we use it to go from psi C to psi C C. So it's the decoder that goes from C plus E, 0 to C plus E C. But okay, actually in the above, we use the inverse of this to kind of erase this C register, or this minus C register. But we essentially need this unitary. This is the key unitary that we use in order to erase this register on top. But this might be overkill, because what we do is take this psi C and we say for each C plus E, for each element of the computational basis of this quantum state, we erase this C. But this could be overkill because we actually need to recover this C not from each C plus E, but from this general quantum state, from this pure state, right? And so this is a totally different problem, potentially a totally different problem, right? And this was actually the key observation of the first Chailloux André paper, right? They said, I'm going to take this function, I'm not going to try to solve it classically, but I'm going to look at it quantumly. So this is how they define, like in the lattice world, the search LWE problem, and that's what they do. So in this talk, I'm not going to talk about this Chailloux André. I'm going to talk about like the most basic way to understand what's going on, and which is in the binary setting, so for binary linear codes, and what we present in this quantum decoding problem. Okay, so now let's abstract everything. So we have this state psi C, which is this superposition, this code word with errors in quantum superposition, and we want to find C, right? So on the left we have what was our classical problem, and on the right we have what is actually the problem we want to solve, right? So we have this quantum pure state, and we want to recover C. Okay, so you have this quantum state. So okay, so if you measure your pure state, you have an instance of the classical decoding problem, and you don't gain anything, right? So this is, we gain no advantage, right? So, and that's why you say, okay, well, what can I do better before measuring? Is there a Hellstrom measurement that would be better? Short answer, no, but we'll see that that there are other things we can do. But okay, so if we measure, we don't win, so we have to do something smarter. And so I'll take as an example the binary symmetric noise of parameter t, which means that each bit, I flip it with probability t. But now I have errors with quantum superposition, so each ci is transformed into this pure state, √1 minus tci plus √t, the bit which is flipped, right? And so, and you take this tensor product, so you have really a product state of which is related to C, right? So that will be my my error noise model, my example. And okay, and so with psi C, how do I do to recover C? So from those two states, if I want to say, okay, as I said, if you want to do the measurement that gives you the maximum probability of measure of CI, then you have to measure in the computational basis, right? They're kind of symmetric, and you have to do Hellstrom measurement that will give you the maximum probability of guessing CI, but that corresponds to classical measuring, and we say that's not good. That's not what we want. And so the idea is that we'll not measure in the computational basis, but we'll do an ambiguous state discrimination. So what is an ambiguous state discrimination? So something that many of you probably know. It's a measurement that, okay, we'll find the correct CI with much smaller probability, but it's never wrong. It's never wrong, but sometimes it can output I don't know. So this I don't know outcome will correspond to this 2 outcome. 2 means, okay, I don't know what it is, but if I measure something, if I measure 0 or 1, I'm always correct, right? So So this is a very simple, like, well-known measurement. And so that means that, okay, Ci, we started from this binary symmetric channel that each bit is flipped with probability t. But now, because we have it in quantum superposition, we can apply another measurement. And instead, we have something that always outputs you the correct bit with some probability and sometimes outputs you from unknown. But that's, if you're a coding theorist, you say, oh, yeah, but of course, yeah, now we're done, right? That's very easy. Because we transform, if we can recover a certain fraction of the bits, like if we're in dimension k, that k plus 1 plus little o of 1, let's say, to make sure that everything is linearly independent, then we know how to recover C very efficiently. We just do Gaussian elimination, whatever, right? Because like random codes, for example, we know that they're hard to decode with the binary symmetric channel, but with erasure channels, like the decoding possibilities are very different and things are much easier, right? So that's the example, right? So on the top, you have kind of the classical problem. You flip a few bits, and you can flip if you have a random code, you can flip 1% of the errors and the problem is very hard. But if instead of this you have errors that, okay, it always outputs the correct value, but sometimes it's value 2, which corresponds to erasure, then it's easy to recover C. And there are many sets of parameters for which this holds, right? And so, which means that, okay, and that's what I call like reshaping the error, is that because you had this binary symmetric channel, and you do a quantum measurement and you transform it to an erasure channel. Okay, so that's the thing. And Chailloux-André, that's what they do. Right? They're in the QRA setting. Okay, in their case, it's a little bit more complicated. They cannot have such a, they cannot do full and ambiguous state discrimination, but they do something partial. They say, okay, with some probability I abort, and with some probability, but if I don't erase, then I know that each bit of Ci, okay, I don't know which one it is with certainty, but that knows it lies in a very small subset of my coordinate space FQ, right? And so, for example, and then you can use the classical Arrogé, but so the size of S must be very small. Think of S as 2. Ci can be or one or the other out of this large field FQ, and then the Arrogé algorithm will allow you to decode, right? So that's what they do. Okay, so, and that's also was kind of this important part. So now I just want to make a recap, is that basically we have this family of quantum algorithms based on Regev's reduction, and you have basically two ideas that we want to do. Or you directly apply a decoder on your function, or, which was done like for structured codes, or you go through reshaping, which, okay, you take your function f, which you won't use this f because the f hat corresponding is what you really want, but you apply this reshaping measurement so that you transform f into another f hat, f tilde, which corresponds to, which you can do somehow unitarily, and that for which the decoder, the classical decoder will work much better, right? Where you transform f into f tilde, this binary symmetric channel, into this erasure channel. Right? And then you go back and you recover the state you want at the end. Okay, but even the second thing, you can, say, so I just reshaped, but then in the end, in some sense, you could have already started from the, from the erasure channel and do the same thing, and that would actually also work. So it's not really a quantum algorithm. So the question is, can you do something which is like really quantum, not only in the reshaping and the errors and applying a classical algorithm, but doing a full quantum algorithm? And so there's a line of work that does this for a very specific case. It's for the belief propagation algorithm for LDPC codes, right? And so it started in 2017. So they did it before anyone kind of thought about this family of quantum algorithms. And so this is a line of work. And if you look at what they do, and like the more recent work by André, so like in 21, what they do actually for LDPC codes is that they construct a real quantum algorithm that does the equivalent of belief propagation, but where the errors are in quantum superposition. And they really send quantum messages and stuff like that. And so, and you have something which is much more powerful that we couldn't achieve with just reshaping and classical decoders, right? So this is really but maybe the only example of a really quantum algorithm that solved like this decoding problem of errors in quantum superposition. Okay, so this I just wanted to mention, and we're kind of trying to get everything together and see what you need, but this is still like a lot work in progress. Okay, so I'll conclude now. Okay. Okay, so this was kind of a recap of what was going on, and now I'll just provide a few open questions. Okay, so we have a very general recipe, structured codes that you can decode in the injective regime, and you hope the problem is hard in the surjective regime. Like you can have a bunch of lists of them, and so so here it was done like for LDPC codes and Reed-Solomon codes, but the question is, if you look at those kind of problems, what will be the most convincing proposal for quantum advantage with this approach? And so this is still very open, right? But it's a natural question to ask, like from this family of algorithm. And except from this belief propagation of quantum messages, we hardly use the nature that the errors are in quantum superposition. But we know from like theoretical analysis and stuff like that, this problem should be much, much easier. So there's something that we're missing. We're not really fully using the quantum nature of the errors in this problem, and so hopefully we could have much more powerful algorithms, right? And so we're just starting, so there is this BPQM approach, but it's very specific for this kind of algorithm, and we have no idea how to, quantize, a general framework for quantizing decoders in order to be more efficient for this quantum decoding problem. On the other hand, we don't know if the problems we're solving, they're really hard. Like, except Yamakawa's André, they prove the hardness within this random Oracle model. Okay, maybe we're just collectively hallucinating, and all of the problems we're trying to solve are easy, and it's just that we're solving problems in some parameters that no one really looked at, and it appears that they're classically easy as well, right? So we have no idea, right, whether it will be a full boom or whether it will be nothing. Okay, other questions, this thing, okay, we're talking about codes and lattices, but we just need a Fourier transform, so it would work for like more general groups, more general Fourier transform. This is a lot of things that I think would be nice to do, and we have no idea like what's going on here. Like, can we do something interesting? Can you provide a reverse reduction? So we said, okay, if we can decode and we can find short code words, can we go the other way around? So, okay, so we'll have some partial results soon about this, but it's also interesting to see like, okay, if the two problems are really equivalent, then okay, it tells us really like what we can achieve and like kind of what's important. And and also one thing to mention is that so there was a paper by Shen last year that claimed to solve to break lattices with quantum algorithm, which used this approach and tweaked it and changed it a little bit. So okay, so the algorithm didn't work out, but still the ideas are nice, and you feel okay, this approach is already very powerful. You don't need you maybe just need one new idea that works to really have much more powerful algorithm, right? So of course, like there is this question, like to change a little, to actually have all of this was kind of follow-ups of kind of what existed, but feels like just one little new idea, and and you could have a very powerful algorithms. And it's things are changing very fast, so there are a lot of things happening, and the deadline of the archive posting of the technical manuscript will be October 10th. So expect to have many more results here. So maybe some of the things I said here will not be true anymore. Maybe we'll have new approach. Maybe some of the problem will be solved. So things are moving very fast. But as I told you, there are many things to do, right? So it's not that most of the things and the more important things will not be solved like by October 10th, definitely. So there are a lot of things to do. It's very exciting, and we don't know whether the purple wave will kind of collapse on the blue region or on the orange region or whatever, or if someone will just remove the little purple dots and just say, yeah, no, that's just a hoax. Like these problems are still hard for quantum computers, and this kind of family of algorithm won't work. So it's a very exciting times, and we really don't know. So it's really open. So yeah, on this, thank you very much for your attention.
So we have time for a couple of questions, maybe. Yeah, at the back.
Thank you for the nice talk. So is your algorithm applicable to the random oracle-based setting in the Yamakawa André? And if yes, what is the implication there?
To which
random oracle-based setting, like Yamakawa André?
Yeah, so that's what they do. I mean, okay, so you mean the general recipe or something?
Yeah, so because your talk is mostly focused on solving, finding a vector with a short norm,
Yeah.
but in the random oracle-based setting, you want to find a vector such that each a symbol is mapped to one under the random function. And I'm wondering if your algorithm is applicable to that setting as well.
So this algorithm is the algorithm they use in some sense, right? So this family of algorithm, they use the exact same framework. So here I did phrase stuff for finding short words, but you could generalize to any region. So you can replace finding a short code word to finding a word which is in some specific region. So yes. So there's no norm. You're not playing with norms. It's just like an easy example to do this. But the framework also applies to what they do. Absolutely, right?
Yeah, I mean, I'm asking about the improvement about the requirement for the decoding capacity. So you only need a soft decoder, and that improvement also applies to that setting as well.
Yeah. So what happens is that where could I find one thing? I want something with f and f hat and if let me just okay. I'll go through the 2 steps of the reduction. Okay, so one example instantiation of something. So the thing is that, for example, for f hat, so basically for f hat, you can take any function. So for example, for f hat, you can take the indicator function over a set t, which has nothing to do with norms and nothing to do. So from f hat, you can take whatever, but still in f, it will still translate to f to something that looks like a decoding problem, right? So even if you take an indicator function over some space, then on f hat, then you know that f, f0 will, there will not be noise in f with some probability. So the structure of the problem you solve in f and of f hat, it doesn't have to be at all of same nature. So you can have on your target problem something which doesn't have anything to do with decoding, finding short code words or whatever, but still the primal problem with f that you're solving is related to a decoding problem.
Okay, thanks.
So it's a very naive question, but I think you have shown the coding problem as some kind of polynomial interpolation problem, and those are very closely related to optimization problems. So do you think like this can be generalized and like these algorithms can be shown as some form of optimization problems?
Yeah, so it's so the open question is, and already in the 2 examples, like with these LDPCs and this Reed Solomon, the problem you're solving, you can phrase it as a short code word problem, but you can phrase it also kind of in a different language, right? Whether it's this Max-Lindset problem or is this a polynomial interpolation problem. So so the short answer is I don't know, but that's also like a very active question is, okay, these problems that don't necessarily look at coding problems, you can solve it with this method. So okay, there could be many more. There could be more of those, and exactly some kind of many optimization problems could be rephrased, and maybe you don't even need the code, but you do need some kind of linear structure. You need some kind of linear structure, but nothing more. So everything that optimization problem that do encompass a linear structure, hopefully can be used. Okay, then okay, I don't know what would be the requirements, but yeah. And this is very open, right? But most probably there would be much more problems that would also fit in this. Yeah.
Thank you.
Thanks for the talk. I have a small question to make sure I understand. So right now, like you assume that the noise you choose is concentrated as Fourier spectrum concentrated on low degree. Is it like when you choose it, I guess that's fine, but like in practice or like typically, are the noise models that people use, do they satisfy that?
Oh no, but we can choose. So we're doing algorithm. I construct the function f such that, right? So of course it's not this noise doesn't come from nature. So of course we do like quantum codes, and these are inspired with coding problems where the noise function comes from nature. But here we do algorithms, and we can do whatever we want.
Yeah, I mean, if the goal is to eventually like maybe also use that kind of techniques to attack existing systems, are the proposals for like things using noises that have that assumption, or is?
Yeah, so we choose f hat, which is exactly the assumption of the crypto system. So basically, here when we chose the small infinity norm is because you have systems like, you have dilithium, it's standardized, and it's based on finding short lattice points of small infinity norm, right? So it's that's the reason why we chose those things, right? It's because it's really related to the noises which are actually used in the crypto system. Of course, there might be other crypto system where it doesn't work that well, right? I mean, it's but yeah, but the goal is that you pick the f hat that is in your crypto system and you try to make it work as best as you can.
Okay, let me just ask one or two questions myself. Thanks for your very nice, interesting talk. So one thing is that, like, I guess if you're looking for low weight code words, you're already in C dual. And since you want to design this f hat so as it actually encompasses some low weight code words, so you must know something about the minimum distance of C dual as well. Otherwise, you will get nothing.
Okay, so sure. So sometimes you have to assume, but yeah, let's just go back to, or maybe the original picture. Yeah. So what happens is that the regimes this kind of approach works on is it's in a very injective regime, so the error in the decoding problem would be much less than, let's say, the maximum error that you can decode from an information theoretic point of view. And so if the error is small for f, the region in the red is really large, right? So the f hat, it's not, so it will not be to the information theoretic limit where maybe you have like one word on average, or maybe you would go below. So you have a lot of margin. You have a lot of margin, and so or when you look at random codes or you look at stuff like that, then it's fine. Another thing is that if you consider the inhomogeneous setting, because anyways you randomize, then you don't even need to know anything about the code, because you know that on average on your shift, the ball is so large that it will have an exponential number of it will have a lot of code words, right? So okay, so you can find counterexamples. Of course, you can find if all your code words are like in a very specific region of space, let's say something like that. But yeah, so you have to do some kind of arguments of this form. But usually the codes we consider, they're kind of very well balanced in the space, and the region red is so large, then we have and another thing, in some sense, if you have a decoder, so if the reduction works, if you have this decoder in the primal, you must have words in the dual code. So you can see it actually as a proof. So you don't need to make the assumption that you have enough code. The algorithm tells you that you find them. If you find them, they exist. So it's also it's not a requirement in the proof of the.
No, I guess you were saying since you want to use this to solve this dual problem. I mean, in the dual space, then you want to design an f hat and then sort of go back to f, find what the f is, and do according to that. But to design the f hat itself will require to make sure that what you get is non-empty. Like it is supported on some small code, short code words.
Yeah, but if you can solve the problem with f, it means that your f hat was not empty.
Okay. That's okay. And one quick last question. So you gave the example of full support Reed-Solomon codes. It wasn't entirely clear to me whether it will also apply to subfield subcodes like BCH codes. Would the same thing work with, say, a BCH code?
Yeah, so it's not explicitly written, but the short, yeah, all of these things work. All of these things work kind of well. So it's not clear, like, what would be the interpretation. But for example, like, if you also go exactly to this kind of multivariate kind of constraints, or if you go exactly to those kind of code. So the short answer is yes, but what precisely does it give? All of these things kind of have to be done, right? It's a lot of, each thing does, each code you consider requires kind of a lot of, does require some work, at least to know like whether the problem you're solving in the dual is indeed hard and stuff like that. Like, so you have to go into like a lossy source coding kind of literature for, to see, and, so so I would say yes, but, it's not done, so I wouldn't know, like maybe there's a specific issue.